Okay, so the talk now is going to be done by Cesar Zapata from IMUSP, São Paulo, and he is going to talk about the Milnor fibration in topological robotics. Thank you very much, Cesar.
Okay, thank you very much. Thanks the organizer for this opportunity to be here in Vitoria. It's a nice city. Thanks a lot. Okay, my thought, I will give in this work a relationship between a new area in algebraic topology. It is called topological robotics. Okay, I will use new results of Milnor fibration to give new results in a specific problems in robotics. Okay, the main of my talk is about this. Okay, I will use Milnor fibration to modeling some situation in robotics and give some solution of that problem. Okay, good. My outline of my thought, I will pay attention in the first part, the motivation, the tasking problem, and the topological complexity in this notion. Is part of the robotics area. The Milnor fibration in that last part, I will use no result, classical results of Milnor fibration. Okay. Okay, the motivation of this talk is in this specific problem, I have this robot arm, okay? And the classical problem in robotics is to planning the motion of this robot arm. How you can control the motion of this, okay? This is the classical problem. How do you can to control this robot arm, okay? Um, a classical boot for this area is the boot of hardware, okay? Um, Specifically, I will use result of manual operations to resolve the motion planning of this robot arm, okay? And this board is part of work together with Tatiana Souza, okay? More details you can to ask me maybe for email, okay? Good. The tasking map planning problem in robotics consists in this. Before to ask, I need to introduce some notation. This is the kinematic map. Suppose we have this robot arm, for example, here, okay? This model of this robot arm consists in 6 degrees of freedom. For example, this part is base, okay? The robot only can to rotate in this plane, and this part only rotate in this plane. This only in this union, también, okay? This joint, okay? In this here, okay? Also, they have the freedom to move linearly here, okay? For that reason, we can control this robot for with 5 parameters. Okay, there exists another extra parameter here. This is the n effector of the robot, but in this situation we don't consider. Okay, so if we are interested to move this parameter such that the n effector, suppose we fix here a specific point. Okay, we're interested to move these points according to the position of this parameter. Okay, for this parameter here, this implies some position of this n effector. Okay, the space which contain these all parameters in this case is a subset of this product. Okay, it is called the state space, or maybe the configuration space in robotics is usually to say it in this way, okay? And another, the point of this n effector, all the possible position of this point here is the workspace, okay? There is the map which assigns state here to a position of the n effector is called the kinematic map. Okay, and generally this map is continuous. Okay, and now here the state space and the work space both are a subset of an Euclidean space. Okay, that's good. Um, the tasking planning problem consists to how to control or how to move this robot R. For example, this R here in this initial position, the in effector is here, but we want to move this robot R such that the final position is this. Now here the in effector position is in this place here. Okay. So in robotics, we looking for algorithms. Okay, these algorithms have an input which consists in a state, initial state of the robot R, and in the desired position for the n effector. Okay, the position in the n effector we means as the task of the robot R. Okay, so the input of that algorithm we are looking for consists in this pair. Okay, we are interested to obtain this algorithm need to assign a continuous motion of this R. It means in topological terms to looking for a path. Okay, in this here is the space of all path, continuous path in the configuration or state space. Okay, the algorithm assigns for this pair a path or a continuous motion in this robot arm. Okay, such that okay this continuous path, the starting point is in A, and the final point is such that when we apply F, we obtain this desired position of the n effector. Okay, the problem is how to construct or design that algorithm. Okay, this is the problem in robotics, specifically in this tasking planning problem. Okay, there is some situations, for example, when node here depends of the kinematic map. Okay, for example, if the kinematic map is a polynomial, it's easy to see that the complexity in general is of this problem is very hard. Okay, so we will use a theory. It is called topological complexity. Okay, to give some information of this problem of tasking problem. Okay, some basic reference is this paper, or in this work, we developed a theory, basic theory of this using some concept. It is called sectional category. Okay. Okay. Just 1 minute. Okay, we can continue here or not. Okay. Okay, I will talk about topological complexity of map in general. Okay. The topological complexity of a map. Okay, obrigado. Is a numerical invariant. Okay, it is given. Okay, a sectional number specifically is given by this. We have here a continuous map. Okay, the sectional number of this map, denoted by this. Okay, is the smallest number such that this space B can be covered with n, okay, with n open subsets with a property over each subset admits a local continuous cross section for this map. Okay, here now this is a local continuous cross section. Okay, the sectional category is similar, but these are at homotopy local cross section. Okay, this is the difference between sectional number and sectional category. We can see that this sectional category is the homotopy version of the sectional number. Okay, for robotics, we're interested in the sectional number. Okay. Okay, some properties of this invariant. Yeah, okay, the sectional category is a lower bound of the sectional number, and it is equal when P is a fibration. Okay, and the sectional number is lower than pullback. Okay, if you suppose here is a pullback, okay, P prime is a pullback of P, the sectional number is less than or equal than sectional number of P. Okay, this is a basic property we will use to construct algorithms. Okay, for that reason, idea of the proof is this. Okay, we want to induce a cross section of this to P prime. Okay, it is possible via the standard pullback. Okay, we suppose here, for example, admits a cross section. We obtain the inverse image of this open subset, okay, of the local cross section, and it's easy to define a cross section for the standard pullback. Then we compose with 8, we obtain a standard cross section for, I'm sorry, a section for P prime. Okay, that is a natural way to induce a section of P for the pullback. Another estimate to this sectional category is another invariant. It is called the category of the Listener-Sherman. Okay. In the case of when P is a null homotopy, these two invariants coincide. Okay, and there is also a algebraic estimate in terms of the cohomology of this map. Okay, but in this situation we don't use. Okay, so mathematically we can study the tasking planning problem. Okay, for that we need to present some notation. Px, recall that the node space of free paths on X. Okay, we consider this fibration. Okay, this is very is well known. And we, for any map, we consider this composition. Okay, so we can define that a tasking planning algorithm is a cross section of the map. Here, a cross section is not a necessarily continuous map satisfying this equality. Okay. And we say that a continuous tasking planning algorithm F exists, imply that space is contractible. It's easy to see, to show this, okay? In general, this space in robotics is not contractible. For that reason, it's not possible to resolve the tasking problem for that system, okay, in general. For that reason, it is natural to define this invariant in terms of the sectional number. Here, okay, the topological complexity of this map is the minimal local algorithms which control the tasking problem by this function. Okay, in terms is the sectional number of this composition. Okay, this is the topological complexity. Okay, there is some properties. The principal property is here. Okay. For that reason, I will present an idea of this proof, okay? It depends to show that this square is a pullback, okay? If I have this pullback, we know how to induce, okay, a section this over this. Note here that a session this is a local algorithm for the tasking problem. Okay. And also, it's classical result that the topological complexity for a sphere is this. Okay. Also, it is known that the motion planning for a sphere is well known. Is this specifically for spheres depend of the parity. If the sphere is odd dimension, we use the existence of field, tangent field over the sphere to define algorithms there, okay? For example, if the 2 points are antipodal, we use the vector field to move in that direction. If there are not antipodal, we use the shortest geodesic to move in that direction, okay? This is in the odd dimensional sphere. In the even dimensional sphere, okay, we use it is known that there exists a field with at least one zero, okay? This is here, okay? In that case, I use a field which is zero in 2 points, okay? With this field, I can to design an algorithm for this sphere. That algorithm will have 3 local algorithms, okay? To design this algorithm is similar, okay? But we need an extra local algorithm, okay? So, about Milnor fibration, okay? It is well known that if I have this analytic margin, okay, with this n more than p, okay, and we satisfy the Milnor conditions A and B, in particular, it is known that there exists a Milnor fibration, okay? In robotics, for a polynomial math, in general, the complexity is bigger. For that reason, we analyze locally, okay, the complexity locally of the tasking problem. For that reason, use the Milnor fibration, okay? So I use this Milnor fibration to give some information of the tasking problem, okay? In particular, with the estimate we presented in the previous slides, it is easy to see that for that fibration over the sphere, okay, we have this inequality, okay? In particularly, the topological complexity for any Milnor fibration with that conditions is 2 or 3, okay? Moreover, we can design algorithms, okay, induced by the algorithms of the sphere over that tasking problem for the Milnor fibration, okay? Specifically, we compute the tasking problem for this situation. This is the Milnor fibration when that mass is the Milnor fibration of a central arrangement, or when f is a holomorphic function here, not necessarily with this condition. And when f is an analytic function here with p even here, not necessarily with an isolated singularity, using the estimates, it is possible to compute the topological complexity of the Milnor fibration, okay, independent of the singularity. Only in this case, when p is even. However, it's more hard to calculate in the fourth case. I only consider p odd and with isolated singular point. In that situation, it is possible to calculate to compute the topological complexity of the Milnor fibration, okay? Moreover, it is easy to design algorithms, okay, for the tasking problem of this Milnor fibration. The open problem is to compute for the other case, when P is odd and with not necessarily isolated singularity, okay? This is a work in progress we are finding out, okay? Okay, that's it. Thank you very much.
Thank you. Very nice talk. Are there any questions or comments from the people that's alive? I have. Cesar, I don't know if you know, but there is a quite very interesting, now I realize that's a quite old work done by Tom Marar and Cathy Hobbs and Chris Gibson from Liverpool in the 90s, 1993, 1994. I believe that they have at least 2 papers working on robotics and singularities.
Yes.
And they use the same model of arm that you are using here. I don't know if you know, I believe that you know this work.
Yes.
Did you use you try to compare your work with them or this work of them or not yet, or there is no comparison, don't know.
This work is in a context in topological complexity theory. In that work, they only study the inverse kinematic problem. That means when there exists specifically the cross section of the Milnor fibration. Okay. Here I study the complexity of the tasking problem when the mapping or the kinematic map is the Milnor fibration. Okay. Okay. Here we are interested to know that topological complexity,
Yeah,
not only the sectional number of the Milnor fibration.
I understand.
Yeah, this is the
So you
okay.
know very well that
Yes.
this good.
Okay.
When you began to talk, I was there at that time. It's not a long time ago, just
Yes.
and I said, "Oh, there is something related. I need to ask him." Okay.
Mhm.
I don't know if there are people in the internet that you want to do some question. We can't see here. If not, so let's thank the speaker again. So we are finished by today. And just a comment. I am here. It's funny because you begin to realize that you are becoming old when you see the people and you say, "Oh, I am the older guy here." It's quite different. I used to be a young boy some time ago. It's funny. But this is not part of your talk, okay? Just a comment that I had the opportunity to remember now, okay? So we meet tomorrow at 9 a.m., okay? Thank you very much. Olha, ele tá mais acabado do que eu, mas eu sou mais velho do que ele.